Welcome. In this video we are going to do a single view reconstruction. So we're going to do 3D reconstruction from a single image. That's a very exciting topic. So these are the results we'll get by the end of this video. So you can see on this first column we'll start from those images. So these are individual ones. So for each column we start with a single image, and then we can generate novel views from different viewpoints. From the viewpoint we can generate a 360 view around the object while we started from a single view. So that's very awesome. We are going to implement this paper from researchers from UC Berkeley on Google Research. Some authors were from the initial NeRF paper. They are pretty well known in that field. So here they're going to use meta learning, and they are going to combine the Reptile paper on NeRF. We've implemented both those papers in that YouTube channel in the past, so you might be interested to have a look first at those two videos individually, and then come back to this video that combines the two principles of Reptile and meta on NeRF. As usual, I will not dive into the paper in detail, but I will directly dive into the implementation. I will put the link of this code into the description. If you find the code useful, please leave a star. Let's move on. So we're going to use PyTorch as usual to implement the paper. We can start by implementing the NeRF class. So here that will be a NeRF that is a bit simpler than usual. It will only be 128. It will only contain 128 hidden units in the hidden layers. On the network will be less deep than usual, and we will not add skip connection, no view dependence. So it's only a simple MLP that takes 120 input units. So these are the positional encoding of the coordinates of the 3D locations, and then we'll put for values the color and the density for each 3D point. Then we can implement the forward pass. We'll just embedded the input to a higher dimensional space to be able to model those high frequencies in the 3D signal, and then we can feed those positional encoded input to the neural network. Then we can apply the appropriate activation function, the sigmoid, to the color so that it's in between 0 and 1, and dilute the opacity because the opacity should be positive. Once we've done that, we can move on to the next function related to 3D, which is the compute accumulated transmittance function that will give you the transmittance along array, and therefore tell you if you've already hit an opaque object or not yet. Once this is done, we can move on to the rendering function. I do not spend much time on those functions because we've implemented them a lot in the past in this channel. And if you are familiar with NeRF, you are aware of those kind of functions. I also have a full course on NeRF about that, so you might be interested. Check it out in the description. So the rendering function takes a model as input, the rays to render HN and HF, which are the near and far bounds for the rays, and then the number of bins, which is the number of bins we'll use to approximate the continuous integral with a quadrature. So first we sample T, some bins along the ray using HN, HF on the number of bins, and then we can add a bit of noise to those sampled values that were deterministic, so that during training we'll not always sample at the same points in the 3D space. We will explore the full space and avoid overfitting. So once we've computed those time T randomly, and that we've computed the difference between successive T that will be useful later to compute the quadrature, we can move on, and we can use those T to compute the 3D locations along the rays. So this is the simple equation of a ray, origin plus times the direction. So we have the origin and direction as input, and we can use the time T to compute the 3D location. Then we can query the neural network at those 3D locations and get the color and density for each point along the ray. Then we can compute the transmittance along each ray using sigma on the delta, and then we can use the right background regularization because we're using synthetic data. We've already talked about that in other videos, so I won't spend time about that, but again, it's just a regularization because we have some white background, but that line 58 could just be removed and you could just return the color. For example, if you have an image with none or white background, you can remove this regularization, but this is a small trick that improves the results with white background images. Then we can move on to, we're almost done with everything related to 3D. Now we will combine that with Reptile. We can prepare our data. Here we will not create a data loader or load the data on the fly, but what we'll do is we will pre-cache everything and then we can query them directly during training on the fly, and that will make training much faster. But you could, if you prefer, just implement a standard PyTorch data loader. So here we take as input the directory that contains the images. Those data also contains the JSON with, for example, some metadata about the images, the parameters of the camera. So yeah, and I will also put the link to download the data. Well, I was going to put the link in the description, but actually the link is already in the README, so you'll have access to the data paths to download them. Then we will have a data set for training and one for testing. So we are taking a flag train. By default, it's set to true. N is equal to the number of images per scene. So during training, we'll use 25 images per scene. But then during inference, we'll only use one image. We take a single image and we do 3D reconstruction from a single image. But during training, to learn this prior, to learn this 3D geometric prior, we use more views per scene. And then we take as input the resolution of the images. For that data set, this is 128 by 128. So we can open the JSON file that contains the information about the data. Actually, the JSON contains it does not contain the metadata directly, as I said, but it rather contains the file path of the images. So for example, yeah, let me double check that. Okay, yeah, so the JSON contains some train on test path for the images. So whether if we are doing training, we load the training image and otherwise the testing image. Then we can iterate over the file that represented in the JSON file. Now we can load the transform for each file. So this actually there is an individual JSON file for each image. So for each scene, we can load the transform that will give us the camera tooled matrix for each camera. So yeah, for now we're just doing that, and now we will move on to loading the images. So we'll cache three variables: the ground truth pixel values, so basically the images. So for each scene we have 25 images of resolution H times W, and of course we have three channels. And then we'll also compute the origin and the direction for the rays for each pixel. So we can iterate over the number of views, 25 in our case by default. We can load the image. We can convert it from we can convert it to a torch, a tensor, do some processing. For example, make sure that it's normalized between 0 and 1. And we can also load the camera tooled matrix. Once this is done, we can also load the focal length of the camera. And once this is done with all the information we needed, we've loaded the image, we've loaded the camera tooled matrix, we've loaded the focal length. And from all that, we can compute the rays on the ground truth pixel values. We have everything we need. So these are the equations to compute a ray from the focal length, from the camera tooled matrix, and from the direction of the camera. So once we finish with those equations, we can cache everything in our variable that were declared on line 66, 76, 77, 78. And finally, we can so at the very beginning, we created 3 lists, line 62, 63, 64, for storing those variables, but for each scene. So every time we see a new scene, we generate those 3 variables. So 25 views per scene, and then we can store everything in those variables, and then we can return those lists. So now we are done with loading the data. We're done with the 3D reconstruction. We can move on to the Reptile part, so to the meta learning. So to do meta learning, we're learning to learn, and therefore during the meta learning loop, the meta learning algorithm, we are not sampling a batch of data, as is usually done in machine learning. With meta learning, we're kind of one step above that. We're sampling a task. So in your outer loop of meta learning, first you sample the task, and then in the inner loop you try to solve that task. And basically meta learning is learning to solve that task. So basically here sampling a task, what does it mean? It means we sample a scene, and then we return the rays on the going through pixel values for that scene, and we will try to solve that scene, to solve that task. Now that we've created this function to sample task, we can move on to implementing the inner loop. So basically this is related to 3D. This is doing the 3D reconstruction on a single task. So basically we receive a task as input, so a scene. That means the rays the rays from the training image, and the going through a color for each ray. So the color for each ray, and basically we're doing a kind of supervised learning to train the neural network on that. So at each epoch, we sample, or at each training iteration, we sample some batch of data, and then we render them. So we feed them in our 3D reconstruction pipeline. Well, in our 3D rendering pipeline that is differentiable. We regenerate some pixel values, we compare them to the ground truth, and we do some gradient update to update the weights of the NeRF model. Okay, and then after we've updated the NeRF model, we can return the new weights, and that will be used in the Reptile algorithm to update the initial weights of the neural network. So yeah, let's move on to the Reptile loop. So basically the Reptile is the outer loop of optimization. What we've just implemented, the perform k training step, is the inner loop of optimization. So Reptile will take the meta model, so the initial weight of the model. So if we go back to the paper, so very quickly, the main goal of meta learning is to learn theta star. So basically it's to learn an initialization, so that when you start from that, you can very easily solve your problem. So basically you are learning some, you are incorporating some prior in the weights of your neural networks, in the weight of your meta initialization. So basically now we've implemented the perform k training step that allows to go from theta star to the orange points, or to go from theta to those orange points. And now the idea is to learn theta star. And you see that going from theta to the images is a pretty lengthy path. And if you start from theta star, it's much faster, so you need to do less training steps, and therefore it's much quicker. But also you've learned some prior. If you try to do reconstruction just starting from theta and with a single image, you will just get some overfitting. You will not get a 3D scene because you don't have enough prior in that region, while we have some in that region that you've learned from a data-driven algorithm. So let's go back to the Reptile algorithm. We're taking as input meta model. So basically these are the weights of the neural network, and we want to learn theta star, so that the weights are in a region of the loss, so that there it's easy to do the reconstruction, and so that there is some prior that has been learned. We take an optimizer for the meta model, and then some extra hyperparameters such as the number of iterations to train the device. We take a function, the sample task function, so that at each iteration we can sample a task, So again, that can be compared to standard machine learning, where we sample a batch of data points at every iteration, but here we do not sample a batch of data points, but a batch of tasks to solve. And then we also take the function, the inner function to optimize, while to run the perform k training step function. On k equal to 32, this is the number of this is k, this is the number of gradient update in the inner loop. So we iterate over a number of epochs. This is usually what we do in machine learning. Then we sample the task. Then we generate a copy of the meta model weights. We generate a new optimizer to solve the k training steps. And then we run the reconstruction with this copy of the model and with this optimizer by calling the perform k training step function. And then we can update phi. So basically we do that with by approximating the gradient with a finite difference. So for example, as opposed to some other meta learning algorithm such as MAML that we've already implemented in that YouTube channel, here we are doing first order gradient update. We're approximating the gradients of the meta model with a finite difference. And now we can put all that together. So we can create our NeRF model. So basically it's our meta model. That's the theta star that we want to optimize. We can load our training data. And then we can launch the Reptile reconstruction for 100,000 steps. We can feed as input the sample task function and also the perform k training step function. And we set k to 32, so the number of gradient update in the inner loop. Then we can also load the data for testing, and then we can test the model that has been learned from the Reptile algorithm. So we will test that on 10 scenes, as we've seen on the README. So we are sampling 10 scenes. From those scenes, we are sampling only one image, and we will test the meta model on those images. So at Inference, we still need to solve a reconstruction algorithm. So as opposed to other approach that do single view reconstruction and that can do that on the fly. So that means that once your model is trained, you just feed your image to the model, and the model, in the same way you can do some prediction by just feeding inputs to MLP. You get directly the output in a few milliseconds. There are some papers that can do that with 3D reconstruction. This one, because we're doing meta learning, you still need to solve an optimization problem at test time. So basically you start from your weights, theta star, and then you solve a reconstruction problem to reconstruct your scene. So basically this is what we're going to do at test time. So basically at test time, what we need to do is to run this perform k training step. We need to run this inner loop to do the reconstruction. So we prepare our data. As we've said, we make a copy of the meta model, and we create an optimizer to perform the k training step function. And once we have everything, we can directly call the function, and that will train our copy of the model. So the NeRF model on line 159, this model will be trained, and then after training, we will get a 3D reconstruction of the scene. So you see, we sample 10 test scene, and then we always take the first image. So during testing, we only test on one image. And then we can plot the results. So once we've trained the model, we can then use the all other views, the 24 other views for testing, and then plot the results. And then we can save the results, and that should give you a figure similar to this one. So yeah, that's very impressive. From a single image, the neural network only has access to those images, and he is able to do this reconstruction with all the prior it has learned during training. So I really hope this video was helpful too. Again, do not. I will put the link to that in the description. If it was helpful too, please leave a thumbs up on the start in that GitHub repository. It really helps. Do not forget that I have a course about NeRF if you're interested. Doing a 3D reconstruction from a single view is one of my expertise. So I will make more videos about that if you're interested. And also do not hesitate to contact me either for consulting or if you are looking for internship in the NeRF research space, Gaussian splatting, on everything related to do reconstruction from single or few views. That's my expertise. So thank you again for having followed this video through the end.